Well, this is a provocative title that comes with actually three dances. One is a dance between wimps and giants. The second one is a dance which we call verifiable boot. And the third one is trying to dance with a persistent adversary that exploits routing bottlenecks in the internet to launch very powerful link flooding attacks, perhaps the most powerful attacks witnessed in the internet to date. So the question is, how do we engage such an adversary, and how do we make sure that the adversary doesn't maintain a persistent advantage over the defender? So basically the idea here is that we have to operate in the presence of the adversary. In other words, no matter what we do, from here till eternity, we'll have to live with the adversary in our systems. So the question is, how do you do that? And the first theme is that, well, we better take advantage of the adversary as well, and of compromised systems to the advantage of the defender. So you probably have heard parts of this presentation before, so I'll go very fast. So first, if we are talking about a dance with the adversary or engaging the adversary, we have to define the adversary. We have to know precisely who the adversary is. So consequently, we need complete and correct definitions of the adversary. So if we have such properties, then there is no surprise. We actually can counter the adversary by denying all the adversarial behaviors. So if we are able to do that, we obviously reduce the defender-adversary symmetry, which was popularized by Donald Rumsfeld, who actually pointed out that the adversary has always an advantage of the defender, meaning that the adversary has to find only one flaw in your system to break in, whereas you have to defend everywhere. Well, so this is a clear asymmetry, and we want to reverse that. And we cannot reverse that no matter what we do unless we have complete and correct definitions of the adversary. So the next thing is, once you know that the adversary is there in your system and your system is compromised, can you actually collaborate with it? Can you take advantage of compromised components? And the answer, you'll see in a minute, that is yes. And we are better off if we collaborate in some clever way with compromised system components. And the question is how? How do you do that? How do you actually ensure that an adversary in your system doesn't take you? So the first question is, can we actually have correct and complete definitions of the adversary? And the answer is no. Certainly not for commodity systems, because such systems will always be very large, or will have large, complex, and functionally rich, perhaps diverse origin components. These things tend to be our giants. These are systems and applications of tens of millions of lines of code. And of course, they are all buggy. And this will be forever. It's not going to change during our lifetimes. And there is a variety of reasons for that. Nevertheless, complete and correct definitions are not possible are impractical for such giants. So some of the reasons why I claim we'll have giants forever is that competitive markets with very low cost of entry, no regulation, and no liability always produce very innovative systems, very price attractive systems, very large, never small. They don't survive. The small ones don't survive. And all these components will have uncertain security properties. So at this point, we can conclude that the adversary will always have an advantage over the defender in the case of giants. Okay, so basically, if you think about it, this no other technology area has, like aerospace and pharmaceuticals and so on, has these characteristics, namely low cost of entry, no regulation, and no liability. So consequently, the pace of innovation here is very high. We become very productive by reusing other people's components, and systems grow very large because of that. We cannot reinvent the wheel. So essentially, we'll have to live with giants. However, it is possible to have complete and correct definitions of the adversary, but only for very small, relatively simple, functionally limited components whose behavior is extremely well understood. And I call those WIMPs. These are systems typically that are under 20,000 lines of code with fairly simple functionality. Now, in the case of WIMPs, we can actually define the adversary behavior completely, and we can counter it completely. We can build in security property in WIMPs that counter that behavior. And in this case, in the case of WIMPs, giants do not have any advantage over the defender. In other words, the inevitable asymmetry is very evitable here for WIMPs. Okay, so now the world is WIMPs and giants. And you've seen this picture before. Basically, the red part are our giants. Red because they are penetrated by the adversary. The green part are our trustworthy components, which have properties which counter all adversary behaviors. And these components, like if you notice in the application, we have a WIMP application. These components are supported by microhypervisor of the kind of which we've seen at Carnegie Mellon before, like TrustVisor, XMHF, and so on. Okay, so the microhypervisor is extremely small and simple. This is between 10,000 lines of code and 20,000 lines of code. Doesn't do much. Maybe has 10 system calls, and that's it. Doesn't process interrupts, by the way. It's all straight line code. And we actually have formal proofs for memory integrity, for example, of the microhypervisor, which were published last year at the IEEE conference. Okay, so it's possible to isolate WIMPs from giants, and that's our architectures of the past 5 years, and others as well. So, so essentially, we know how to do that. Separation kernels, microhypervisors, security kernels, hypervisors, all these are these very small components that provide you with WIMPs eventually. All right, so the application, isolated applications that we have are crypto libraries, for example, for key management, secure keys of various web servers, secure crypto channels are provided by WIMPs. Application reference monitors are provided by integrity checking, WIMPs implemented, meaning that WIMPs can implement integrity checking of the giant application behavior. Okay, so WIMPs have been used in practice. In fact, the last one, integrity checking of giant services, this is something that most software producers are either thinking about or having already. And I'm talking about companies like Samsung, Google, even Microsoft will have this in the future. Sony Ericsson, they're all building components like this one here, simply for checking the integrity of the giant code, but not necessarily the full security properties. Okay, so this, we know how to do this. We know how to do the isolation, at least in principle. The problem is that WIMPs do not survive. Those little green WIMPs. Why not? Because they lack basic services. They don't do much, so they can't have basic services. Like what? They don't include file systems. File systems are large. You cannot put them in WIMPs and claim that you know all the security properties. You don't have isolated input-output in WIMPs and claim that they are small, right? So you don't have I/O services. Well, you don't have network services in WIMPs. And you don't even have persistent memory in WIMPs. So what are they good for? Well, without all the services, they are not good for anything, right? So they won't survive. And by the way, these are serious reasons why WIMPs have not been implemented by software manufacturers so far. So the question is, how do you provide the services for WIMPs? So one way to do it is to actually blow up your green part of the operating system and include all the services in them and call that the green machine. This is the machine, the red-green separation that Butler Lamson typically talks about. And that's what he advertised around 2009 in this communication of the ACM paper. Well, that doesn't quite work for us because these WIMPs are becoming green giants, and consequently they are not going to be much better than the commodity operating system. So that's not going to work. What's the other place where you can put all those services that we're talking about? Well, let's try the microhypervisor. Well, that's not very good either, because the microhypervisor will blow up, and it will not be micro at all, and it will lose its security properties. So essentially what we have to do is to build what we call wimpy kernels that actually take advantage of the services provided by the red penetrated system by outsourcing the services and verifying their results. So that's a dance that we are suggesting. In other words, export all functionality that is too large to be verified into the penetrated giant, into the insecure giant, and verify the results of the functionality. If you can do that, you don't need to protect those services if, of course, you can always verify the results. You don't need to trust the adversary control giant. So the idea is that we can also implement some services in here by exporting some code in the application WIMPs themselves. And essentially, this wimpy kernel here is a wimpy kernel that we designed for input-output with character-oriented devices, USB devices. So what we did, we took roughly a 20,000 lines of code USB component, and we restructured it, and we reduced it to about between 2,000 and 3,000 lines of code here. And we exported all the other services in the operating system and verified the results. We did that only for services that could be verified, otherwise they are not exportable. Okay, so essentially what you see in this picture, that we added this green part on the side to any commodity operating system. We added the security services on the side, and we made them collaborate with the untrusted services. So if you can verify results, you don't have to trust. Contrary to what Ronald Reagan used to say. He used to say, trust by verify. Well, that makes no sense. If you can verify, you don't have to trust, right? So anyway, that's what we do here. So the example that we had was this USB subsystem, and we exported the USB hierarchy verification and device initialization, and we could actually verify that. And we reduced the USB component to about 3,000 lines of code from about 20. We did that in the past with the PCI subsystem, which was dramatically reduced. And you can see the details of this design at the IEEE Security and Privacy Conference this year. It was presented in May, this design of the wimpy kernel and the WIMP giant separation. So that's the first dance. Collaborate with your adversary if you can always verify the results of the adversary provides to you. You don't have to trust the adversary. Okay, so the second dance is equally interesting. Let me go back to this dance just to introduce the second. So basically, this is great. If we can do it, we are in business. We can actually add security properties to insecure commodity systems. And this could be anything. It could be Windows, could be Linux, could be your iOS, could be any commodity operating system that doesn't have to be verified. But notice what happens. What happens on the hardware here? Notice that you are sharing the hardware with your untrusted operating system. So this microhypervisor somehow has to be booted. Right? So the question is, how do you do that? How do you make sure that when the microhypervisor boots, it boots in a malware-free state? In other words, the malware from here is not already on your system. Okay, so that's the second dance. We call this sharing the same dance platform with the adversary and performing what we call verifiable boot. So let me describe the problem and then outline a solution. So this is the verifiable boot part. So essentially, verifiable boot says that you have a system that has the typical components, has a local memory, has some peripheral devices that have memory and processing, network interface cards that have memory and processing as well, and connected to a network. And somewhere in the network there is a verifier. And the verifier wants to basically show that the system is booted in a secure state. So for that we have something called secure boot, which says that the device has some authorized configuration, namely that it was booted from a set of vetted system components. Then we have trusted boot, which says that the boot took place in a sequence, which is called measured boot or trusted boot. And verifiable boot says that you do trusted boot or secure boot in a malware-free device. So when the boot is done, you know that the system is in a malware-free state. Okay, so how do you do that? Well, we have Professor Moriarty to deal with, who is probably the most potent adversary ever known, at least to fiction. And Moriarty controls your network, controls your device, controls your peripherals and network interface card. At that point, Holmes tries to verify that the system is in a secure state. And of course, this is nearly impossible. You can only do it probabilistically. So we try to simplify the problem to say, look, Moriarty doesn't control your network because the verifier is local, is close to the system. The verifier is actually a system that you plug in the system to be verified, right? So Moriarty cannot come in the middle between the verifier and the system being verified. So essentially the game we play here, or the dance that we have here, is called flip it, right? So Moriarty takes over your system through the network, and you want to flip back the control over your system, and you do a verifiable boot. At this point, Moriarty is out, and you compute for a while, and Moriarty takes the system over again at some point because of probably a bug, a 0 day that you didn't know about. And you might notice that that's the case. You do a verifiable boot, even if you don't notice. Once in a while, it's good to do a verifiable boot. The Moriarty is out for a while. So you flip the system between you and your adversary. That's the dance that we are advocating here. You have feasible recourse if you are a defender. Right now, we don't have feasible recourse. We are completely clueless as to whether or not our system is controlled by our adversary. And there is no way to determine that one way or another. Antivirus, anti-malware, anti-all these things, we know how well they work already. Okay, so that's the second dance, is verifiable boot. So the question is, verifiable boot is hard because it's about proving negatives. Meaning you have to prove that when you boot from the verifier or from some external device that you control, you are in a malware-free state, and your peripherals are in a malware-free state. So you need, first, we start out with what we call untampered program execution. So basically what that says is that you show that the execution of some special program runs in a malware-free random access memory states. So you still don't know anything about the peripherals, but you know that whatever runs here is malware-free. The memory is malware-free. Okay, so that's the first stage. The second stage is that you have to show that your peripheral devices are clean. And then in the third stage, we have to have an uninterruptible sequence of booting your vetted software. This is software that's demonstrably clean. In other words, you have an image of the software on the verifier, and you have a fingerprint of it, and you collect the fingerprint of the software that you boot here from your device, which was previously controlled by the adversary. The verifier compares the two fingerprints and enables boot. Okay, so that's basically the notion of verifiable boot. And the way this happens in a real implementation would be like this. First, the verifier sends a message to the prover device that's under the control of the adversary. This fellow here is completely controlled by the adversary. So the verifier tells the adversary, please initialize the memory to a random sequence of bits which I send you. And the verifier knows the sequence of bits, and that cannot be changed by the adversary. And initialize the prover code. In other words, load this code that I'm sending you, adversary. And that prover's code is a very fancy checksum function. And there is a communication function, of course, because they have to communicate. And there is a hash function and the reboot function. So this is all the code. All this code that you see here, it's roughly about 12,000 lines of code or less. So for example, the hash function has roughly about 1,200 machine language instruction. Okay, so essentially now the adversary runs your proof of code and waits for the next instruction from the verifier. The verifier sends a random nonce. That's a random number that doesn't repeat. We don't do it often enough to repeat it. And based on that, the checksum produces an unpredictable result, a result that cannot be predicted before the checksum runs on the nonce. Okay, so, and that's timed. In other words, the checksum now disables the interrupt, computes a checksum over the entire memory, which of course was filled with random numbers, including these functions themselves, including the checksum code itself. And at the end, it sends back the result to the verifier. That result is timed. In other words, if there's any deviation from the flow of control or any instruction deletion or insertion, the time will go wrong because this is a loop that goes n log n, where n is the number of words that you have in the memory. So it's a very large loop. This story, the first implementation, which is not very efficient, is about 10 minutes on the 512 megabytes of memory. Right? We can optimize it probably to about 3 minutes. But this is timed. And you have to show also, which is very interesting, you have to show that this checksum on the adversary control cannot communicate to secondary storage or with external devices. That's not easy. So we have not handled it yet. We know how to do it, but we haven't handled yet the proxy attack, where this checksum is run on a much faster machine and the result comes back in time or even earlier. We know how to fix that, I mean, how to cope with the problem, which is recognized in the literature. Okay, so if the checksum comes on time, the verifier, of course, verifies the checksum value and latency and says, okay, send me the hash. So now an untimed sequence, the checksum transfers control to the hash function that reads the boot image, sends back the hash result to the verifier. The verifier verifies the hash result. And if the verification fails, then there is a golden image that's transferred from the verifier to the device. If it doesn't fail, the boot sequence starts. And the boot image is loaded from the secondary storage. Okay, so what's the problem with it? Absolutely no problem if it worked well, if we have evidence that it works. And so far, no one has ever proved formally that this stuff works. In other words, there is a model which was proven, but the model is completely out of this world. It has unimplementable assumptions, not our model. So there is no proof that this was all heuristics. So for example, heuristically, you argue that this checksum function cannot be compressed. There is a heuristic argument which also says that not only the timing cannot be compressed, but the memory cannot be compressed. In other words, the adversary who receives this code cannot compress it. Of course, the adversary cannot compress a random sequence or a pseudo-random sequence very much, right? You can't compress pseudo-random sequences very well at all. But the code itself might be able to be optimized by the adversary who gets it. It could even get a copy of it ahead of time and optimize it offline and load it in before it runs anything. So there are all sorts of heuristic arguments for this, but there is no formal method or formal argument of correctness here. That's one of the things that we are doing now. We are trying to construct checksums which are provably correct. I mean, mathematically provably correct, so that the adversary will even try to optimize them. But right now this works. We have confidence that very skilled people will not be able to break this. But all that means is that there are no obvious flaws. Skilled people come with obvious flaws and sometimes even non-obvious ones. So we are quite confident that what we've done so far works, but we don't have a proof. and it's very likely that this has to be reduct. In other words, that if we want formal arguments, this should be thrown away and we should move to something else. Anyway, so now the third dance, and I'll take another 5 minutes and stop. The third dance is something interesting that we haven't published yet, but we'll present this next in about 2 weeks. So basically, what we try to do here is to defend against a fundamental property of the internet. This is called routing bottlenecks. So what's that? So suppose that you have a bunch of destination addresses here, B, and a bunch of sources of messages, right? So it turns out that in the internet there are what we call min cuts. These are cuts, they are not your regular graph min cuts. These are cuts in all the routes from the sources to the destination. So a min cut is the smallest set of links, right, on the routes that you can cut to disconnect all the communication between the sources and destinations. That's fine. This is no problem. Usually the min cut is large enough, cannot be flooded or cannot be attacked. But the problem is that what we found is that all these min cuts for any group of destination in the internet have routing bottlenecks. The bottlenecks are small set of links in the min cut that can disconnect the majority of the routes, such as 80% of the routes. So for example, the min cut might have 200 links and the bottleneck has 10. And these 10 links disconnect 80% or 90% of the route communication. Now, is this a bottleneck of sorts? And it's not a bandwidth bottleneck. Under normal mode of operation, all these routes are well provisioned. There is no problem. Except that your adversary can concentrate messages in this area about the same time, flooding maybe between 10 and 20 links, and most of your communication is finished. And it's finished for a very long time. So these are the most powerful type of denial of service attacks witnessed to date. So the question is, how pervasive are these? What caused them, and how they defend them? So I'll just show you something about pervasiveness and the fundamental causes, why they're built in the internet, and defense will leave it at that, since I only have about 3 more minutes. Okay, so basically we looked at about 15 countries and 15 cities, by the way, not in these countries, but in others like China, the United States, and others. And in these 15 countries, we picked 1,000 servers at random. So one of the things that we noticed is that when we trace all the routes from a variety of sources in the internet, we found their min cuts and their links, your bottleneck links. So bottleneck links appear when you start ranking the links in terms of their popularity. So routes to links, popularity of links. And we found that there was a very distinct power law in the popularity of links. Some links were extremely popular, very few of them. So if you look at this area here and you blow it up, you'll see that here we have 13 links which are very, very popular, and most of the others are not. Okay, so if you flood those 13 links, you take out a large percentage of all the traffic. So we modeled this with a zip Mandelbrot distribution. This is link occurrence or link popularity, and we found these parameters of the curve fitting, and so that's the zip Mandelbrot distribution. Alpha tells you what kind of power law you have. So the smaller the alpha, the better off you have. The bottleneck is not very severe. The larger the alpha, the worst case you are. So these are the 15 countries that you did. By the way, Western Europe had the least problems. Eastern Europe, Middle East, and Asia had the most problems. So anyway, so the point is that we had this link flooding attack, which I'll not describe, but it's very persistent. You can cut 40 to 80% of the traffic. And here are the degradations that we've seen in these countries. Not that much degradation here. At 20 links, you have about 40% degradations in the UK, right? Which does among the best. UK is one of the better countries. But here, at 20 links, you get slightly over 80%. Guess which country this was? So let me just remind you about those countries. So these are the countries here. So you have Brazil, Egypt, France, Germany, India, Iran, Israel, Italy, Japan, Romania, Russia, South Korea, Taiwan, Turkey, and the United Kingdom. So the best one was, I think, the UK, if I remember correctly. Which one was this? So worst in this. So this is a country which is supposedly flooding US banks, right? Which one is that? Iran, right? They have a miserable infrastructure with respect to link flooding. I mean, 1,000 servers in Iran can be, the connection to the rest of the world can be cut off by about 80%. Okay, so the fundamental causes are cost minimization. We can't get rid of this problem. We can ameliorate it. Obviously, Western Europe is doing better than the Middle East and Asia. And the United States, by the way, also. So basically, if you look at inter-AS routes, you'll find that always the minimum dollars dominate, right? And in intra-AS cases, you have route cost minimization, which also tells you which routes you are going to take. Okay, so clearly, since inter and intra AS communication is done based on minimum cost, you'll have this power law distribution between senders and receivers. These are not your topology power laws, they are routing power laws. Okay, so we showed this in this paper with these experiments, and then we looked at reductions of this problem. So we had these operational procedures that we can apply and reduce, for example, the degradation. If we ameliorate the inter-AS communication, we reduce degradation by about 20%, intra-AS by another 20%. And we found that the tier 1 and tier 2 networks account for over 90% of the problem. So you're not talking about the little guys, you're talking about the big guys who do route optimization. So somehow we have to engage the botnets and the adversary that amplifies attacks. And an attack like this was observed against flooding links, was observed about a year ago before we published our first paper, by about 2 weeks. But their attack was sort of a dumb version in the sense that it could be noticed easily. Our attack, called the crossfire attack, cannot be noticed at this point by any ISPs because it's distributed, cannot be handled by any ISPs. It's distributed across ISPs. We pump traffic and we back off because we find multiple bottlenecks. So we send traffic to a bottleneck, and then 180 seconds we back off. We send it to the second bottleneck for the same target. We back off, and this can go on forever. Right now there is no solution. Okay, so that's basically what I had to say. This research, of course, is going on. It's not finished in all these areas. And next year we'll report probably a provably correct, verifiable boot operation. So thanks.